So today's speaker is Dr. Martin Gerlach. Martin conducted his PhD research at the Max Planck Institute for Physics of Complex Systems in Dresden, under the supervision of Eduardo Altman. After finishing his PhD in 2016, Martin Gerlach was awarded a postdoctoral fellowship at Northwestern University in the group of Professor Luis Amaral. Dr. Gerlach has published articles on topics ranging from kicked electrons to statistical laws in linguistics, and today he will be telling us about the cutting-edge machine learning at the Wikimedia Foundation. So thank you very much for joining us today, Martin, and with these words, the virtual floor is yours.
Thank you so much, David, for the introduction. I have to share my screen, right? We tried this, it should work, but yes. Can you see my slides?
Yep, perfect, yeah.
Great, yes, thanks a lot for the invitation. It's really an honor to be here to present and share my work here at Physics Department. Again, that's, so my background is originally in physics. I can say a word about that too. I will not talk much about physics or about quantum information. I'm curious to learn from you too, but I hope to give more generally maybe an overview of some of the work we do actually at Wikimedia Foundation, and especially related to machine learning. I hope it's not only interesting, but also convey that it's actually important to do. David said, I'm a research scientist at Wikimedia Foundation. What is Wikimedia Foundation? It's an organization, a non-profit that operates Wikipedia and many of its sister projects, Wikimedia Commons, Wikidata, Wiktionary, and so on. Before I start with the slides, I want to just briefly point out that what I say here today is not necessarily, is my personal view, not necessarily of the Wikimedia Foundation. I also want to say that Wikipedia and the Wikimedia movement is highly distributed system. So there's hundreds of thousands of volunteers. So I will also not speak for them, even though I consider myself part of this committee. And yes, if you have clarifying questions during the talk, I think David will moderate, but if there's really something pressing that doesn't make sense, please interrupt and I will try to clarify. Yeah, I mentioned my background is in physics. Maybe it's not so obvious. How did I end up at Wikimedia Foundation or at Wikipedia? So I will say that my background is, I studied actually physics and I did my PhD to study dynamics of complex social systems and trying to apply the methods, mathematical methods to study language change. For example, how do new words change? And in my postdoc, I then went actually a little bit further and tried to take language as a marker and study how scientific disciplines evolve and how is scientific knowledge actually produced. And then from this, it was actually not such a big step to join Wikimedia Foundation as a research scientist anymore. So that just as a background, that to give a little bit of sense, but coming to Wikipedia or Wikimedia, and Wikipedia specifically, the largest project, maybe the most common, most well-known project in the Wikimedia ecosystem. Wikipedia is the largest encyclopedia in the history of humankind. It exists in more than 300 languages. There's more than 55 million articles, more than 10 million monthly edits, and more than 20 billion page views per month. So it's in the top 10 of the most accessed websites in the world. And this all became from a small idea just in 20 years, but in these 20 years, it didn't just grow enormously in the number of articles in all these numbers, but it has also become an extremely important part in the information ecosystems. So for example, for online learning, Wikipedia has become one of the major educational resources. So there's a recent survey showed that Wikipedia ranks number 2 or 3, just behind YouTube, how in this service, how adults learn online. It has also it's not just about entertainment or films or movies, but even for very serious topics around medical knowledge, Wikipedia is the #1 place to go for health information on the internet, and even for doctors, sometimes not just for potential patients, which is maybe good and maybe not, I don't know. Also, it powers many technologies such as, for example, if you think of the knowledge panel in Google search, this is usually powered by Wikipedia, but also speech assistants such as Amazon's Alexa highly depends on the information provided by Wikipedia. In the fight for disinformation, so many platforms recently are under much more scrutiny to do more about misinformation and disinformation. And in many cases, they directly rely on Wikipedia for the good or for the bad. One can think it's good because they, for example, put links to relevant Wikipedia articles for videos about flat Earth theory, for example. On a negative part, one could say, well, maybe this is just outsourcing this problem to the volunteer community. And there's many more examples from Twitter, Facebook that essentially try to view Wikipedia as a ground truth, which is not, for sure, it's not perfect, but it plays a very important part. And it has even gone so far that people have described Wikipedia as the last best place on the internet for a model as a community-based platform. And maybe going more into the direction of an application of science or science of machine learning, Wikipedia, which is maybe not so obvious, plays a huge role as a data source for modern day machine learning. So all of the major large language models make extensive use of Wikipedia for training. So this is the training data. So BERT models, XML models, more than half the data is from Wikipedia dumps. But even for other language models such as GPT-3, they might not include specifically Wikipedia, but they often use resources such as Common Crawl, which is, I think, one of the largest resources of text. An analysis shows that the second most common domain in this corpus is Wikipedia. So even implicitly, this plays a very big role, and this is good that it plays such a big role. And we could now ask, well, this is great, so there's nothing to do. What is the problem? What should we actually work on? What's the problem to solve in Wikipedia? And one direction that actually this does not come from us, from the foundation, but from the whole movement, the volunteers, about 5 years ago, they sat together and said, what is the strategic direction we want to work on? Where should we improve? And they defined the problem of knowledge equity. And this means, in short, essentially breaking down the barrier, the social, political, and technical barriers, preventing people from accessing and contributing to free knowledge. This might sound a little bit abstract, but I'll show you in what does it mean in practice. And this map maybe gives an example, and this is a map of the world for articles in English Wikipedia, around 1 million articles that have a geolocation, so a GPS coordinate. And each article is a dot. And then you see that there's some Europe and North America that have a lot of these dots. So there's a lot of coverage of these regions. But there's many, many, many regions in the world, Latin America, Africa, Asia. You can, almost all of it essentially is essentially dark. So we are missing this knowledge about these regions. So, and this is only English Wikipedia. You can go to most of the other languages, and you will see a very similar picture. So it means we are actually very, very far from capturing all the world's knowledge. And this brings us to the question, well, what is actually knowledge? Knowledge is socially constructed. So we have to go beyond the actual content, but also consider who produces this content and who consumes this content. And as an example, we can take to make this a little bit more clear is the Wikipedia gender gap. And this has received a lot of media attention in the last 10 years, rightly so. And this started from the observation of the content that if you take all the biographies in Wikipedia, so men and women, there's around, it's like we're very far from parity if you look in coverage of biographies. This might have many different reasons. So less than 20% of biographies are about women. Seems very low. But it becomes more clear if you think who creates this knowledge. And we know from surveys that less than 50% of editors identify as women. And what has been very surprising in recent research that we have been doing, that even on the reader side, even among readers, women comprise around 1/3 of readers and account for even less of that from the page views. So we have to, in order to understand what are the barriers or what is the knowledge that is not captured, we actually have to capture readers and contributors. And one model that has been shaping our thinking around is this pipeline of online participation, so that from the whole of internet users that could potentially contribute knowledge, only a tiny fraction condensates then as the knowledge that is represented in Wikipedia. And we would like to improve, remove these barriers and have a better coverage. How do we do this? This is our research program that we call Addressing Knowledge Gaps. And this is essentially operationalizing equity into more atomic and measurable units, which we call knowledge gaps. So as in the beginning of this program, we built a taxonomy on the left, and I will not go in detail, but it's a systematic overview of different areas where knowledge gaps appear. And we consider 3 main dimensions, which is the content itself, but also contributors and also readers. One example of this is the gender gap, but there's many other components such as geography, language, socioeconomic factors, cultural background, and many, many more. We also attempt to systematically measure these gaps, so to keep track whether we are actually improving over time to close these gaps. And as a third point, we are actually trying to build tools to bridge these gaps. And I will focus today on one example or two, how we are supporting work to bridge this gap. And I want to note that this is maybe not obvious, that Wikimedia Foundation does not edit the content itself. So we cannot now go and say, let's create, each of us creates art biographies about notable women. No, we don't touch the content. We only provide infrastructure around it to host the projects. And one way we want to bridge this gap is the development of a machine learning tool called link recommendation. And the problem is the following, that editing is hard. There's many barriers to editing. They are technical, conceptual, like what should I even do, and cultural interaction with others. And these barriers filter out many people who could be great editors, but for whom the current workflow is not a good fit. And to diversify our contributors, we need to diversify the ways we contribute. The solution we came up with other teams in the foundation is to break down editing into simpler tasks, structured tasks, so that are easier to understand, they're easier to do on a mobile device, and where it's easier to get a positive editing experience. And link recommendation is an ideal candidate. It's very well defined. So you add a link. It's a frequent task type. It's very attractive to users, and there's a very low risk for vandalism. And how we do this is to implement this in a machine in the loop way, so that models are designed to only play a supporting role to support the improved capacity of editors. Editors should always keep full control of what to do with these recommendations. And it implies that we should be mindful about interpretability and simplicity of the models. What is the link recommendation task then? Is essentially we have to do this at scale. We have to generate link recommendations at scale, and this corresponds to an entity linking task. So we have to parse Wikipedia text, identify a mention, so an unlinked piece of text. We have to generate a set of candidate links, and then we have to disambiguate and select the correct one, which could be not to link that specific word. There's some specific challenges in the context of Wikipedia around this. So it's a well-studied task in machine learning. However, in Wikipedia, there's more than 300 language versions. So we have to think of ways how can we build models that in principle can support all 300 of these languages, because the highest impact of such a model will not be English. It will probably be smaller communities in which there is not a lot of data to learn with. It's under-resourced languages and so on. And there's other considerations about each Wikipedia has a different manual of style and so on. But just going through the model in what does it mean? So the first step is dimension detection. So we parse the text and we generate an anchor dictionary from parsing all existing links in a Wikipedia dump. This is the text and the target link. And then we just use some string matching techniques to scan unlinked text and match, did we already find previously a similar piece of text in our anchor dictionary? And if yes, this is a good candidate. As a second step, we have to generate candidate links. So having scanned all the possible links that exist in a Wikipedia, we can then look up whether this piece of text, what are possible links in which this was already used. And we do several types of filtering to remove certain constraints. So we don't want to link to disambiguation pages and so on. Or the community asked to not link to articles on names or articles on dates, and we try to incorporate this type of constraint-based, type-based constraints, and implement a bunch of other heuristics. And we then need to disambiguate between the different candidate links. For this, we use a set of features. For example, how often have we seen this link before? How different is the title and the page we want to link to? And even some representation, some representation about the article, semantic representation we use to identify how similar is the source and the target article. And for using these features, we essentially extract fully linked sentences from existing articles and generate positive examples. So these are link mentions with the correct link, and we extract negative examples that are link mentions with an incorrect link or mentions that are not linked at all. And then we just train a rather simple binary classifier to say, is this a good candidate or not? And with this model, we create having this model, we have can generate these recommendations at scale and implement in some user interface. Just to give an idea, this exists in practice. I will talk about this, but you actually get a suggestion. You just ask here, this should be added or not. You evaluate this, the user evaluates this, and then this is saved as an actual edit or not. And you can easily do this on a mobile device. And the question is, or from the evaluation, we can fairly say, yes, it works. So we did automatic evaluation, but also manual evaluation with pilot wikis in Arabic, Bengali, Czech, and Vietnamese. And it's not perfect. The main variable here, evaluation metric, is precision. That is around at least 75%, around 70% to 75%. This was our lower threshold to say here the recommendation should not be too bad, or the editors should not see too many wrong recommendations. And with this input from the manual evaluation, this was actually deployed to or was tested in several Wikipedias, and it showed that it was very popular, this task, among editors. So they make many more edits. Editors make much fewer mistakes. So in Wikipedia, edits can be reverted by other editors, and the revert rate was substantially reduced from these structured tasks versus unstructured tasks. And also editors stay around much longer after they sign up to create an account. So the activation rate is increased from around 20% to 24%. 4% might not seem like a lot in absolute terms, but this can easily translate into hundreds of additional new editors that get recruited. And this was deemed very successful. So we have deployed this currently in 10 wikis. So if you go to any of these languages, create an account, you can do these newcomer tasks. And we are currently planning to deploy this for 10 and more Wikipedias. And of course, this was only kind of a prototype test. Adding links is not so, the focus there was not so much of the edit content, but more the action of the edit. But there's many other tasks where ML, machine learning approaches, can generate recommendations at scale. And currently we are working to recommend images. So many articles, more than half of articles in Wikipedia lack images. So this is an ideal candidate. And one can think of many other tasks as well, adding references to improve quality of articles, adding sections to expand, making it more readable, to do copy editing, and so on. And this is all in the planning. And if you're curious to learn more about this type of work, I added the link here. But with this, I want to take a short break. Maybe say, before I go to the next topic, and ask if there's any major questions here, David. I don't know if you're monitoring. If there are
I've
any.
not seen any in the chat. It's been incredibly clear and easy to follow. So I think maybe people are holding off to a discussion later on.
Okay, just wanted to, before rushing through, wanted to make sure that, because now is a good time to stop. Great. So
Thanks.
Thanks, David. In the second part, I want to talk about a related technical problem. So it's about the problem of topic modeling or topic models. And this is a technical challenge that feeds into many of the other problems that we are facing as like an underlying problem. And what is topic models, or what is topic modeling? And it's essentially the problem of how to organize a large collection of text into clusters, or like automatically organizing this. So, and large here, I mean millions of documents. Wikipedia, all the Wikipedias has more than 55 million articles. I think English alone has more than 6. And every month we have 250,000 new articles that are being added. So what are these articles about? How can we classify them into meaningful groups? And just from the scale, it's clear that we need automatic approaches for that. There's a limitation that there's essentially no good existing annotations that are already there, maybe by the editors. They are either incomplete or very impractical, such as categories. So many people might know the categories, but the actual category system in Wikipedia is really, for this type, at least for, it's usable for some things, but for this, it's not very usable. There's millions of, or more than 1 million different categories. It's completely inconsistent across languages. And so in this case, this is not very useful. And why we also want to, yeah.
Sorry, Martin, I have a question here. So someone else, can you mention a little bit about the size of the data that Wikipedia handles in various instances of their work?
It depends what, so we have content. So these are the scale, what I described here. This is the amount of art, like the number of articles. You can, and this is public. We have this is shared. There is edit data. So every edit is saved, and this is also public, and it's about, I think, English Wikipedia is around 1 to 2 edits per second. So, but this adds up, right? So this is a huge, this becomes already quite large if you want to see how it changes over time. Once you go to the level of readers, so we track essentially whenever there's a reader loads a page, this is a page request. This is not public data, but we get a request to our servers. This data is huge. This is terabytes, right? So, or even more. I don't even know, but this is then handled internally. You cannot run this on a single machine anymore. So this is then a huge distributed cluster, distributed file system that you can even work with. This data is extremely large. Does this answer the question?
I think so, yeah. I think maybe well, I can't put words in the mouth of the person asking, but I think maybe the person was after that kind of what on average is the kind of data weight of one article, and how often, I guess you answered how often they kind of update and requests, but
it varies a lot. So some articles get updated a lot, right? So there's hundreds of people. Some articles never get updated after years. So there's no good, but there is a lot of edits every. So yeah, English Wikipedia is around 2 edits per second. You have other projects like Wikidata. This is, I am not sure what is the edit rate. I can share if you want to get a sense how frequent they're updated. I put this here in the chat. This is a visual interface where you can see how fast projects get updated. And we have a sister project, Wikidata, which is a knowledge graph. So you store information in machine readable format in the form of triples. So an item has a property, and that property has a value, which is another item. And this gets updated orders of magnitude faster. So there's, I would have to check here, but it's probably 10 or 100 of edits per second. And this scale is quite challenging to keep the system up. And there's dedicated teams in traffic that try to maintain and make sure that we can actually work with this data. And from the editor's perspective, there's another component of, or another area of work that we work in to support editors. So there's to make sure that the edits are not, make sure the quality remains high so that edits are not vandalizing Wikipedia. And what editors do is there's a type of editor called the patroller. So they patrol, essentially there's a feed you can go through and see all the changes as they appear right now. And they essentially go through this one by one. But then there's only so much, like once the rate increases above a threshold, you cannot keep up anymore to go through every single edit and kind of pick them apart and say good edit, bad edit, good edit, bad edit. So our team is also building tools to help editors kind of, or flag these edits and say, here, this edit is probably good, here, this edit, so you probably don't need to pay attention to that one, or already flag an edit and say, here, this is probably a vandalism edit, and there's some signatures you can exploit to make it easier for them to cope with the scale of this. And this is a big challenge. Yeah.
Thanks a lot, Martin. I think that's clear.
Cool. Okay, where was I? Yes, topic models. Yes, how to organize texts into clusters. And we know that topics are very useful because we know that, especially, for example, in the link recommendation, we know that editors don't want to work on any article. They have specific topic interests. So they are motivated to work on specific areas. So we would like to surface articles around specific areas that they would like to contribute to. So, but how we do this with this scope? There's one approach that we pursue, which I call the easy approach, because it's kind of a supervised approach. And this is why I call it topic classification. And the aim here is we assign an article to, or for each article, we want to assign a label out of a set of predefined topics. And one useful reference or one useful resource we use here is something that's called wiki projects. And this is editors organize themselves in so-called wiki projects. So there's a wiki project medicine, and there they organize all the articles around medicine. You can see this when you click on the talk page of that specific article in which wiki project this is categorized. There's thousands of these wiki projects, but actually the community, the editors have organized these wiki projects in a directory structure. So we can now, with the help of this directory structure, we can map these thousands of wiki projects into a set of 64 high-level topics. So these are, for example, biography, history and science, films, libraries and information. I don't mention all 64, but these are the classes. And this is our ground truth data, so to say, of like, this is topic labels. And now the problem is, how can we build a model to assign or predict whether a topic label should be assigned to every article in Wikipedia? Because not all of these articles are tagged, not all languages use these tags. So just relying on the editors is not enough, but it's a good starting point as a ground truth. So what we do is, and keep in mind, we want to do this for all languages. So we essentially want to try to avoid as much any language specific parsing. So what we do is we take the Wikipedia article and strip almost everything. And it might seem crude, but essentially we only keep the outlinks. So the blue links you see in an article. Why we only keep the blue links? Because the blue links, we can map those links to a language independent identifier. And this identifier is what is called a Q item. And this is the representation of this concept in the Wikidata knowledge graph. And this is the same ID for these articles, independent of which language they are used in. And based on this, just keeping these IDs in each article, we can learn a language independent embedding, a language independent representation of these articles, and then use these representations as features to build a classifier. And then for any article, we can make a topic prediction of whether it belongs to one of these 64 topics. And what is the result? Yes, it works. We can cover really almost every single article across all of the 300 languages in Wikipedia. So the criterion is there a link, and is there at least one link? So more than 99% of articles we can cover. It's a very simple model, but this is, in this case, is a feature to cover these languages, but also is a feature for deployment, because you might think Wikipedia is very well known, but we are not Facebook and we're not Google in terms of hosting services either and maintaining things. And from evaluation, we also did automatic and manual evaluation on a held out data set and with expert editors in the respective communities. And we are in almost every case, we are essentially, with this very simplistic language agnostic model, we are performing usually almost as good within 1 or 2% of very language specific models. And you can actually, if you want to see how this works, you can go to Wikipedia search. If you use the search, there is a keyword you can use. It's called article topic. And you can here, I searched for article topic of physics. So if you search for specific articles and you just want articles around a specific topics, you can specify, and this is consuming these article predictions. And this is currently being deployed from switching language specific models to these language agnostic models. But this is the easy part. This is the thing that is deployed that we already use in Wikipedia. But actually, what happens? I want to now go to the hard part. What happens if you want a more granular view beyond just 64 predefined topics? And it's a much harder problem, since you typically want to find the topics that are contained in your data. And this is an unsupervised problem, and typically is approached in terms of a dimensionality reduction problem. So you take the Word document matrix. So this is how often each word in your data appears in each document. This is a matrix, very sparse, and you try to approximate this matrix in a matrix decomposition using some latent variables, and the latent variables are your topics. You define a generative model and infer those parameters. One of the most common approaches here is latent Dirichlet allocation. The details are not so important, but it's the most, it's highly influential, has more than 40,000 citations in 20 years. So this is used everywhere if you want to model topics, but there's a bunch of well-known problems until now, and is how do you choose the number of latent dimensions? Or in your generative model, how you choose the priors. And in a specific case, you use so-called Dirichlet priors, but this is not justified by any understanding of the real world. It's just a mathematical convenience, so to say. There's a bunch of many more problems, and we try to make a contribution in solving some of these problems by formulating a network approach to this. So instead of modeling this, so we formulate this as a network. So instead of this matrix, we formulated a bipartite network. So where you have two types of nodes, these are words and documents, and you put a link whenever a word appears in a document. And now we formulate this problem of topic modeling as a community detection in complex networks. Specifically, we approximate these network using a generative model called relying on stochastic block models, where we essentially approximate the adjacency matrix with blocks where nodes are assigned to blocks. And what we showed is it's not just an analogy in which we solve a similar problem, and I, respecting time, I will not go through the details, but it's a formal connection between topic modeling and community detection. And we can actually show that it's a more general and more principled approach in which we can solve many of the intrinsic problems of latent Dirichlet allocation. For example, is completely non-parametric approach. So we don't commit to Dirichlet priors. And it's also completely hierarchical in the terms of not having to choose the number of free parameters, such as the number of topics. And we can use efficient inference algorithms based on Markov chain Monte Carlo. And just to give you one idea of the type of problem we are solving,
Martin, maybe just before
problem of a topic mixture and
Martin?
the Dirichlet. Yes.
Sorry, just maybe before we move on to this slide, I had a question on the previous slide.
Here?
Yeah, so an anonymous attendee in the chat has asked me, is this completely unsupervised, or do you use any user input to determine? Okay, let's see. So the person is asking, if you're using sparse methods, you might need to reduce the impact of highly prevalent words like the and of. Do you not use any input from the person running the algorithm to lower the significance of these words?
So the answer is it's completely unsupervised. And this is actually typically there are some of these pre-processing steps that people remove specific words to deal with sparsity or because they are not informative. And actually our approach can deal with this automatically. So it comes out in the analysis, these types of words that are typically removed by hand by some heuristics, they fall out as a separate cluster of words. And then you can just remove that by hand, but it comes out in an unsupervised way. You don't need to know that beforehand.
Okay, thanks a lot, Martin. And then there is a second question, if you don't mind. So Haumo Yuan, hi Haumo, he's asking about the update of these that you mentioned before, that these articles continuously are updating. So he says, will the topics continue to change then frequently as the updating is happening? And would this, like, you know, what would be the machine learning cost and calculation time be of continuously updating the topics?
This is a very good question. Yes, the topics do change, not very much. The main problem, I think, what is more relevant here is new articles that are being created. I don't know the numbers exactly, but I would assume that since we have 250,000 new articles each month, you want to assign those two topics too. Yeah, and maybe editors haven't had a chance to assign them to relevant topics. And for this, we can then rerun the model, and this is actually not very costly. So this is a very simple model. Takes, I don't know, a few hours on a simple machine. But this is actually, in this case, it is a feature that we can support more languages, and we can frequently update as kind of with every month new dumps are being created. We can in bulk learn this model. Yeah.
Thank you.
Cool. I was here. Topic mixtures. So what is a topic mixture? It's typically how you think a document is a mixture of different topics. And for just to visualize, I assume here we have 3 topics. Yeah, topic 1, topic 2, topic 3. And now this simplex, what you see on the left, is essentially each point would correspond to a different topic mixture. So if you're in the middle, each topic is represented with 1/3, 1/3, 1/3. And if you go into each of the corners, the topic mixture would skew towards one and only one topic. Now, the Dirichlet distribution essentially assumes, or the Dirichlet model assumes, that documents are sampled from a Dirichlet distribution. And it's a very restricting distribution, which is essentially unimodal, can have 2 different shapes, which you see on the right, on the top, or at the bottom. And depending on the parameters that you choose, so either you're in the corners or you're located in one part of the simplex. And the question is, like, this is an assumption. Does this match reality? We don't know. And why we use it is only for computational convenience, since it's like in a detail, this is a conjugate prior for the multinomial that's used in the generative model. And this becomes very bad if you assume, well, what happens if you have a non-Dirichlet topic mixture? So let's say your collection of documents is not peaked around one specific peak, but there's different types of mixtures that you can have. And if you want to infer this distribution with latent Dirichlet allocation, you infer something completely different. This is on the top. So left is the ground truth. This is synthetic data. Then we plug this into LDA. We'll get something that's completely off. And not by incidence, what you will see will match something a little bit closer to latent Dirichlet allocation, but this is because this is the prior distribution that you put in. Whereas if you use our network approach model, you almost exactly infer the specific distribution that you put in. And there's many other cases where you will see the same. And this is just one example case how this Dirichlet assumption can just lead you into the completely wrong direction. And if we run then this model on real data, I'll just briefly show that we have this bipartite network of documents and words, and we find this is an example of where we run this on Wikipedia articles from 3 different groups: chemical physics, experimental physics, and computational biology, completely unsupervised. We didn't choose anything. And you get a clustering of documents. Here you get 2 main groups around physics and biology articles on the left. And then as you go down the hierarchy, it gets more fine-grained. And on the right, you get 3 types of groups, 3 types of clusters, and one corresponds to words, biology words, one group corresponds to physics words, and one group corresponds to these not like words that are not related to a specific topic, like what you call stop words, is the of end. And this comes out naturally here, and we don't need to remove this by hand. And just as a last slide, we have recently extended this framework to not only model text. Usually you have other information as well, such as links or metadata. And we have extended a framework where we can incorporate these different types of data in the same framework using multi-layer networks. So each different type of data would then just correspond to a different layer in this network. But so just to say, if that is interesting, so, and usually this is the case, there is a way to just naturally apply what we have already proposed to incorporate that too. But I will not go into details, and I will stop here with this. Happy to take more questions. I will only add a closing remark, which is if you're interested in any of this research, we're happy to get in touch with you in many of the different ways. So we have a public mailing list, join our conversation. You can follow our research newsletter, or on Twitter, we have a handle to get updates on the latest research in the Wikimedia world. We have monthly office hours where the team is just available to chat about anything that you want to bring up research-wise. And we have showcases similar to this seminar. These are monthly seminars. We have a workshop, a wiki workshop, which is held at the web conference. If there's some, you can submit there. We have also research funds for which you can apply. And finally, you can also contribute by editing Wikipedia or donating. And as a final recommendation, please free your knowledge. So any code, data, or papers you have, if you can, use a free license so it can be reused for Wikimedia projects and by others. And with this, I want to thank you for your attention, and thank you again for the invitation. You can reach out to me with any follow-up questions, and I want to thank my collaborators at Wikimedia, but also at external collaborators. And yeah, happy to take further questions.
Thanks, Martin. I see that Professor Barnes has a question, so I'll just hand it over to him.
Oh, yes. So I use Wikipedia actually a lot for my teaching, so hopefully you're pleased to hear that. It's terrifically useful. Well, what I've found over the years is that the way that I want the information is somehow sometimes different than the way that, for example, a mathematician might want it. And so you see with certain articles, they start off being written by physicists, but then over time they gradually sort of converge on a more mathematical description, which is then using notation that I'm perhaps less familiar with. And the question I have, though, is sort of more generally about how the user can in some way specify their background to be able to control what they see, the order of the article, or how the article is constructed, and from what information it's constructed, and whether that's even a notion for Wikipedia or not.
So first, I'm great to hear you use Wikipedia for teaching. I think this is a challenge to convince people, or there are programs to encourage teachers in developing countries, for example, to use Wikipedia for teaching, and maybe they use it for teaching, but then they don't recommend their students to use it as well. So that's important to kind of familiarize with them how to use this as a research and how to be critical and so on. Related to the specific question, that is indeed, so this is a big problem, and to go like kind of one sidestep is not just around kind of mathematician's view or a physicist's view, but we know, and I don't know if I should stop sharing the slides, that maybe we can see each other.
I think the slides are gone.
The slides are gone. Okay, cool.
Yeah.
Is around that we know that the contributors who contribute are also highly educated, and they write in a way that is often way too difficult for the average level of education of readers. So that many readers actually, if you think of, so we can measure readability, for example, and content is too difficult. So how there is thinking, how can we, what would be a way to make it consumable to people that might not have 5 years or of college education, and then this is difficult. Related to this,
I think you do need to keep both, though. You can't say, because sometimes you'll go to a web page and you're an absolute specialist in it, and you just want some kind of detail, or you want to see, I present this in my lecture course, how are they presenting it here? But sometimes I'm very interested in language, so I go and have a look at a page on some ancient language or something like that, and you know I'm having to look up every second word.
Exactly. So, and this is that we know that people come for very different, the motivations why people come to look up are very different. Like it's very broad, like can be very different. It's not just students or fact checkers, but it's very broad. There is a problem around kind of this customization of Wikipedia. So there's a strong, essentially one core feature is that Wikipedia is the same no matter who looks it up. Like it's not like Facebook's feed or Twitter's feed, which is customized based on in some way that is very opaque, is not transparent. And this is how I believe it. This is my personal opinion. I think this is a very strong feature of Wikipedia, that you don't have this customization where you then have reinforcement mechanisms that lead you to specific types of contents. Nevertheless, I think there are opportunities or to explore ideas around how readers can customize content for themselves. So if you say I want to have only a very coarse view, you might only get presented like a summary, for example, a very broad summary. Whereas if you select here, I want to get a deep dive, you already, the different section gets loaded and you become aware of the full length article, which sometimes is very, very long. So these are ideas that are being explored, or we are researching what are the different needs of readers and what could be possible tools in which to support. But it's very early. It's on a very, we don't have this on a.
This may sound a bit primitive, but I mean, there could be like a background button. You click on it, a menu appears, and you go, you know, Bozo expert. I don't know.
It is. You would be surprised. It is like changes to interface are difficult
I'm sure they are.
And how you make those decisions. So it is not very centralized in a sense that this can be just decided. So there needs to be community consensus that this is something they would want to have. So these are always, there's always questions around governance of these things and how you decide how this should be done and so on. But yes, it is, yeah.
And I should stop now because I think there are many other people who want to ask questions.
Norman, you're up next.
Okay. Thanks, Martin. That was a very nice talk. Thanks for coming. It was good that you came over. I had many questions, but maybe just one. How's the interaction between you at Wikimedia Research and the community? How does that work? So how does it reflect in your daily researcher's life? Was something I was quite interested in.
It happens on many different levels. So we have, like, we try to build venues where we interact with, like, give them opportunities to interact with us directly. So we have office hours where we essentially just have a chat. Anyone can join and they hear, I have this question. How does this work? Right? Can you help us? We have, there's workshops, there is mailing list, like there's different ways in which people can just come and ask questions, ask for support. There's meetings, hackathons, community events where we typically try to participate and see what are, like, especially around developers. So there's a different type of community that is not actually editing maybe the content, but they write tools to do certain things, bots, and maybe how we could support them with using machine learning techniques there. So we're trying actively to reach out to them and try to see what are their needs and how we can support them. But that's really on a almost weekly basis. I would say that there's different touch points where we can interact with them and we try to reach out. We always have to be kind of aware that these are volunteers. So you can also not overwhelm them with, here, give us feedback around this, give us feedback around this. Like, this is essentially, they have a day job, 8 hours, and then they do all of this. So we have to be very mindful in how we, like, not creating more overhead around this.
David, how are you on time and other questions? If there is space for another question, I'd ask another question if there are many other questions.
I have one more question.
Okay.
And then, but like, I think, Norman, take your time, do your question, and then I'll ask my question. I can't see any more hands up at the moment. I see one from Hugo. So okay, let's do 1 or 2 minutes each, and then I think we conclude after that. Okay. Yeah, I was just wondering if you have any, since this is usually a quantum information seminar, do you have any algorithms you can recommend where you have troubles that quantum information scientists maybe should look at to come up with crazy ideas once quantum computers are there?
So I must say, I am very ignorant around quantum information. So please correct me if I'm wrong, but what I understand is the promise is it can make things very fast, right? So that things we might say in terms of computational complexity, this is difficult. Yeah. We can, yeah. So I think these inference algorithms we developed around inference of stochastic block models, I think this is a very principled approach, but it's not, at least the way we have so far worked with it, this is on a much more experimental level. So we know it works really, really well, much better. Like, it's much more robust than many of these ad hoc solutions. But in my research, I have not been able to run this on, like, large, like, millions of articles, for example, it's just because it takes too long. The inference is too time consuming. But I think more and more in the community around complex networks, I think it's been realized that this stochastic block modeling is a very, very powerful approach. So it's a very general framework to capture structure in networks, and networks can capture different types of interactions. But typically this very fine level you're not interested in. You want to abstract this to a more a more high level system. And these block models tell you something about the mesoscale or large scale structure that exists in these networks. And often these correspond to different functional groups, like stop word groups in these language examples. But in biological networks, it might correspond to different drug-drug interactions, or I don't know. So this is then beyond mine, but it's a very general and powerful approach. So I learned about this 5, 6, 7 years ago, and I think it's a very, yeah, I think it's not only mathematically very robust, but the results so far have shown that if you want to capture interactions in terms of networks and you want to model the structure, this is for me the way to go. Like that is very robust, and I think this is now a consensus in the network community that these block models are just yeah, powerful. So if there's a way to do quantum inference of block models, I don't know if that is possible. I would be very happy.
Thanks. Yeah, thanks a lot. So I guess I'll hand over to the next person.
Yeah, I was just Googling. I just Googled quantum inference block models, and I couldn't find something exactly like that. But there's a quantum probability model of causal reasoning, and quantum probabilistic models revisited, the case of disjunction effects in cognition. So some people are thinking about this. It's published in extremely dodgy journals, though. So maybe there's scope for doing something non-dodgy. Hugo, go ahead.
Yeah, so this was a great talk, first of all, and I had a question related to sort of the ethics that you might consider in your machine learning models. So you mentioned that Google and YouTube use Wikipedia as sort of the source of truth, especially for controversial topics. But with, I mean, aggregate knowledge and machine learning models, you can introduce biases that come with your training models or with the data that you're feeding into it. So is there any consideration for how Wikipedia chooses what is true especially in a controversial topic? Or how to avoid
I think this is the $1 million question that you are raising there. What is true? And it's a challenge. So there's no general answer that we say this is how we choose it. We cannot, first of all, like we as the scientists, we cannot choose. The foundation cannot choose. There's always a consensus in the community, and it's not voting, it's not democracy. This is a rule. So there has to be a consensus around what the community accepts as truth. We can help them to figure out or make better informed decisions about this. These are tools, but it's not to decide. And you can already see this, that different language versions capture information very differently, especially around contentious topics, around specific conflicts, and even now with conflict, for example, in Ukraine, coverage might differ substantially across the different Wikipedias, and we have seen that there's a specific case around in Croatian Wikipedia that was essentially taken over by a small group of people that tried to insert facts around a very revisionist, like portraying revisionist history. And this can be there. So we have to this can happen. We're not immune to this. And we have to, I think, find out what are good markers, how we could, what are markers that the information is reliable or not. So it's not just because it's there, it doesn't mean it's true, but there's different kind of signatures that the chance that it's true, or at least not wrong, is higher. And one case is often that if you have a more diverse set of contributors, more people looking at things, the chance that it's factually wrong is much, much lower. So one way is to, yes, diversify, but also diversify in terms of the speakers, for example, like having people from different regions speaking the same language, contributing to the same place. And then they have to find a consensus, and you cannot bias this in a completely different ways. And there's different types of mechanisms how communities try to ensure this, but this, yeah, it's.
And I guess, just not to take up too much time, but in terms of the algorithms, so you kind of have these language independent markers, but clearly certain languages like English will dominate in terms of data, and other languages will have fewer data. So do you see that you need to sort of weight languages differently, because there will be ambiguities in some where sort of English might just eat up all the small ones, and that categorization becomes sort of an English driven one?
Yes, this is always then the problem, that like one issue is around how you like that English will in many cases dominate just from the sheer data. You could easily say, okay, then I train a different model for Hindi Wikipedia, for example, which is much smaller. But then you might run into the problem that there's not a lot of available data. And as an example, we did build a model to identify sentences in Wikipedia that require a citation. So the policy is every fact that could potentially be discussed or put in question should be supported by a reference, yeah, to ensure, like, here, there's a reference, you could look it up if it's true or not. And you can build language models for that. And for English, this is fairly easy, not fairly easy, but it's possible to do with some accuracy, to say here, there's probably many sentences that one should take a look if there is a citation for that or not. Like, someone should add a citation here. But then once you go to the other languages, using, for example, modern language, large language models, outside of English, this might, or in many cases, doesn't work so well. And then you really have to question, is it worth to invest into a technology, or to build a model that in the end will only support English Wikipedia? And from an equity perspective, that's probably not a very good decision, because from the very start, you exclude millions of potential users or actual users. And then, so this is how, from the beginning, you have to decide, okay, how we formalize the model, maybe in English, you could do it much, much better, but then in other languages, you could do nothing. So that is at the very first. And we then have to resort and rely on other tools that might not work as well, but we can support in a broader base and support more languages. Yeah.
All right, thank you.
So I see there is a question from Chris Long. He says, first, thank you for a great talk. My question is, how do you label the categories you generate through your new block model?
Yes, there's no, so in this case, this is a problem with unsupervised approaches that you will always run into, that you get the blocks or the topics, like the clusters, and there's no labeling that comes from that. You could then look, a priori it's just an index. So this is group number 1, group number 2, group number 3. This is with a problem that appears in any clustering problem, any unsupervised clustering problem. So, and we cannot solve this problem. And I don't think there's, just from this inference, you can solve it. You can only say, okay, what can I then look into these clusters and look at what are properties that are very common among the documents, for example, that exist in this cluster by looking at the titles, or I don't know, but this is some post-processing you would have to still do. This is true, but this is a general problem in any unsupervised clustering approach.
Thank you, Martin. I think we've already overrun quite a lot, but like I think people, including myself, thought it was extremely interesting to hear about this web page that we're all using all the time for various things. I remember, you know, when I was a kid and Wikipedia kind of started to be a thing, the teacher said, like, told us in school, like, oh, there's some interesting articles about the history of your hometown here, but you can never use this for anything academic or scientific. And now I think we live in a world where everyone almost exclusively uses Wikipedia to look up small things, and it's the first go-to thing for anything before. So it's impressive how quickly that happened. I think maybe just if you have a quick answer, if you don't know worries, but like what I'd be interested in is maybe what's the kind of next big thing on Wikipedia. I've noticed that there's some kind of, it's not workshop-like, but there's some, like, you can find recipes for foods or cocktails and stuff like this on some Wikipedia articles. Now, I wanted to ask, is there something coming up on Wikipedia in terms of different learning things?
You mean topic-wise, like specific topics that are being introduced? Or
well, the new thing that I noticed was that you could find these instructions of how to do something on Wikipedia, which I don't know, maybe I'm wrong, but for me that looked like a new thing. For example, you Google it, you Google beef stroganoff, and you get a Wikipedia article on the recipe of beef stroganoff, and it tells you kind of, you know, how to prepare it. But maybe that's a one-off example, or are you expanding in any way like this?
So we are not expanding in this at all, in the sense that the actual content, we are not contributing in this way. So we are providing infrastructure, and even what should be included in Wikipedia, for example, we also don't decide. This also is decided by the community. So the volunteers, that they decide what is notable, this is a criterion, and what is not notable. And this can even vary across different languages. So some language community might consider recipes should come in, other consider maybe this should not come in. So I don't have a good answer, I think, for the specific question around this. I can say what are initiatives around like different infrastructures. So there's Wikipedia, for example, is just one project around encyclopedic articles. And there's other projects like Wiktionary around lexemes, or I think you have Wikivoyage, you have Wikisource, Wiki to scan documents. So there's a bunch of these different projects that are not exactly encyclopedic. And at least for us, one big aim we have for the future is to better understand these other projects and how we can understand this. One, for example, is WikiCommons, that supports all the multimedia files, and it's a huge database of millions and millions of files or videos and presentations. And how can we better integrate this in Wikipedia to surface, for example, images for image recommendation, or Wikidata, which is this knowledge graph, which allows for a lot of this language agnostic modeling, because you can connect language specific articles to concepts that are encoded, or you can encode information in a way that doesn't depend on the language anymore. So you just state facts as triples of IDs and properties, and you don't actually need natural language anymore. Or Wikisource, where you have actual documents, source documents, how could, and for example, communities or digitize actual records, handwritten records from archives, digitizing them, and how they could serve to back up facts like to verify claims in Wikipedia, and how this could better feed into that. So that is from an infrastructure perspective, at least what we are very much interested in, how that is not just around this encyclopedia, but also that there's many things around this encyclopedia, learning with images, how to understand reliability of information based on sources. What could these sources be? And so on. And the whole component around languages. I think these are very at the heart, at least, of our thinking.
Interesting. So thanks a lot, Martin. We've run over kind of massively now. So thank you very much for coming. Please let us know if you're around in the UK at some point. We'll give you a lab tour and go to the pub. Yeah. For the other people on the call, we'll see you next week for the last seminar of this term, and then we will be hearing about quantum biology.